Great. So I want to talk about online transaction processing, which is near and dear to my heart. I'm Mike Stonebreaker. I'm at MIT. I also work for a variety of startups, including a company called VoltDB. There will be a couple slides, words from our sponsor later on in the talk. So what did OLTP used to look like? Well, I was around in 1985. In fact, I have plenty of gray hair. I was around in the 70s. So remember how you used to buy airplane tickets 25 years ago. So you called up a phone number, you talked to a human, professional intermediary, a terminal operator, who submitted the transaction on your behalf. And that's the way things worked in 85, which meant commerce went at the speed of the professional intermediary. Now, 1985 was also an interesting year because that was the first year a conference called the High Performance Transaction Processing Workshop, HPTS, was run. Jim Gray started that conference, and the whole goal at the time was to do 1,000 transactions a second. And in 1985, that was an unbelievable stretch goal because commercial systems were doing about 30 transactions a second. So the whole goal, 25 years ago, was to get from 30 to 1,000. Now everyone knows that 1,000 transactions a second can be done with one hand and both feet tied up. So it's now considered totally easy, as we'll soon see. But anyway, that was the speed people were expecting and the stretch goal in 1985. And that's because OLTP went at the speed of humans. Of course, things have changed a little bit since 1985. First of all, the internet has disintermediated this professional terminal operator. You go to Orbitz or to one of the airline sites and you buy tickets directly. You no longer talk with an intermediary. So the intermediary has been replaced by an end user, who I affectionately call Aunt Martha. And this change has sent transaction volume just through the roof. So the internet allows all of us to do transactions. We no longer need to go through a funnel called a professional human. So that sends volume way up. Second thing that sends volume way up is PDAs. So, and other kinds of sensors. Your cell phone is a transaction originator. You can buy airline tickets from your cell phone. Everything on the planet is in the process of being geopositioned by your cell phone or other sensors. So the bibs of marathon runners have a sensor in them to detect position and keep people from cheating. All the insurance vendors are following the lead of Progressive, and they're putting a sensor in your car and rewarding you for good driving with lower insurance rates. Again, this just sends volume through the roof. So in the last 25 years, online doesn't mean human anymore. It means a much broader class of database-oriented applications, and the tsunami that we are in the middle of is often not human-generated, although sometimes it is. Transactions now don't necessarily mean a human, buying a widget. So it doesn't mean merely, you saying buy it from Amazon. And so there's a much broader class of transactions that we have to worry about. And then the third thing is that in 1985, the standard wisdom was, well, if there was a crash, you just got back up again as quickly as you can. And you were willing to take whatever downtime was required to read the database log, put stuff back together. No one is willing to take downtime anymore. Everyone wants to run backup and have high availability, switch over to a backup, tandem style. And this is now, table stakes for online transaction processing. So just for some examples of what new OLTP looks like, well, any of you who play, who will admit to playing multi-user internet games, maintaining the state of such multiplayer, massively parallel games is an online transaction problem, which is the state has to be persistent. You can't lose it. You can't screw it up. It's high performance OLTP. Vendors are very quickly, especially the web guys, are really quickly moving to real-time mass personalization in ad placement, which is at the speed of clicks, figure out what ad you want to put on a page and put it there. That's straight OLTP. Although the stock market volume on Wall Street is going through the roof, and that creates a nightmare for those guys in terms of electronic trading. There's another application that is becoming increasingly prevalent, and that's risk management. One large electronic trading company is trading all over the world with independent electronic trading desks, and the CEO wants to maintain in real time, meaning millisecond by millisecond, what is his exposure to any given event, like a stock going up or down, or a currency going up or down, and all of this is risk management. If you want to do real-time fraud detection, real-time intrusion detection, denial of service attacks, this all looks like new OLTP. So the new OLTP world is not 1,000 transactions a second, it's 1,000,000 transactions a second. So you need to ingest a fire hose in real time, and the fire hose is usually a collection of messages, each of which turns into a transaction. And you need to do standard OLTP at 3 orders of magnitude better performance than 1985. And as often as not, you have to do this transaction volume is intermixed with random queries. What is my exposure to IBM right now? So this is what you need to do. So now the question is, well, how to do it? So there are 3 solutions, as near as I can tell. Of course, there's a 4th solution, which is roll your own code on top of the bare metal. But I will dismiss that one out of hand since I'm the database guy and I'm interested in seeing people use tools. So there's 3 choices. The first one is you can go to your favorite legacy relational database vendor, and the major choices are Microsoft, Oracle, and IBM. So I'll call those guys Old SQL because they were all around in 1985 selling database systems, and they're still selling database systems 25 years later, generally running on very elderly code lines. So that's one option. Second option is to say, let's buy into the pitch from the NoSQL vendors, which is give up SQL and give up ACID in order to go fast and to scale. So that's option 2. And then there's an option 3, which I call NewSQL, which takes the position SQL and ACID are good. It's just the implementations from the legacy vendors that are screwed up. And so go fast by doing a totally different implementation than what the legacy guys do. So I'm going to spend the rest of the talk discussing these 3 options. And I should say right up front, I'm a NewSQL advocate, so you'll know where my position is. So I love to dump on the elephants. The traditional SQL vendors, I affectionately call them the elephants. They all have code lines that date from the 1980s. This is elderly legacy code. In the world of database systems, the problem is whenever you put in a feature, you can't take it out. So they are grow-only code lines that are, at this point, I would call bloatware. And as we'll soon see, they're not very good at doing anything anymore. And what that means is that they can be beaten by between 1 and 2 orders of magnitude by something else in every vertical market I can think of. So they are trying to be one size fits all, and in the process, they have one size fits nothing. So they are no good at doing anything. And specifically, if you ask them to do 1 million transactions a second, it's just way outside what they can possibly do. So they give you mediocre performance on the new world of OLTP. Now, if you want to do 30 transactions a second or even 1,000 transactions a second, performance doesn't really matter. So at the low end, you don't care. Have at it if you want to continue to run the elephants. But otherwise, you've got a serious performance problem. Now, when I say the elephants are no good at anything, I love to caricature them with the following graphic. Imagine the entire world of database applications. So if you have a database application, put it in this triangle. In round numbers, the market goes thirdsies to OLTP, historical data warehouses, and then everything else. Lay down on this triangle another axis, which is how much you care about performance. So in the middle of this triangle, you don't care much about performance, and at the 3 vertexes, you care a lot about performance. So you guys, may well run database applications, and it fits somewhere in this triangle. So here's the problem that I see that the elephants have. At high performance, there's something that kills them by 2 orders of magnitude, which means that if they respond in a minute, something else will respond in a second. And I'll talk about in OLTP how you do that. But it's true everywhere I can think of. In the data warehouse market, all the elephants are selling you what are called row stores. They store data row by row by row on disk. And it's well understood that column stores are a factor of 50 or 100 faster than row stores in the data warehouse market. So if you want to go fast in a data warehouse, run a column store. If you want to run open source, run Hadoop. There's lots of options. None of them the elephants. In the everything else world, there are array database systems, there are graph database systems, there are document database systems. In the science world, arrays work way better than tables. Again, something else beats the heck out of the elephants. So at the high end, everywhere I look, there's something else that's a much better idea. At the low end, you might as well save a few bucks and run MySQL or Ingress or Postgres or some other open source system and save some money. So I see the elephants hemmed in at the low end by open source, and at the high end by something else that's wildly faster. So over time, I see them getting only the crevices in this triangle, but I see them, just in a world of hurt long term. So you say, give me some detail on why it is that they're in a world of hurt in OLTP. Well, it turns out that if you run TPCC, TPCC is buying parts from warehouses. It's a very well-known standard benchmark. And unless you are at the unbelievably high end, this is a main memory application. So, the standard sizes that people run TPCC at are, 10 gigabytes, 100 gigabytes. Hardly anybody, has a real-world example of TPCC on a terabyte database. So this is an example of TPCC on 10 gigabytes, which, by the way, think of as main memory because it fits in main memory. This thing that I'm running these slides on doesn't quite have 10 gigs, but it's getting pretty close. So the servers you guys all are running have wildly more than enough memory to put TPCC at the 10 gig level in main memory. So we instrumented a vanilla open source DBMS, looks exactly like the Elephant's code lines. We'd have run one of the Elephant's products if we could have gotten the source code so that we could have done the instrumentation, but they of course don't hand that out. So this is on the Shore DBMS written at Wisconsin. It runs roughly the same way the Elephants run. So we instrumented the code and says, where do all the cycles go if stuff is in main memory? So this isn't exactly true because it depended on exactly which of the TPCC transactions you're actually doing, and there's a fair amount of detail and complexity. There's a paper called Through the OLTP Looking Glass that a bunch of us wrote in SIGMOD 2008. So go there if you want the gory details. But at a high level, here's what we found out. Useful work is a very, very, very small percentage of everything. It's under 10%. In this drawing, I've shown it at 4%. The other 96% is something else. And it more or less divides equally into 4 big consumers of overhead. The first one is running the buffer pool. Even though your data is in main memory, Shore and all the Elephant's products are disk-based systems. So what happens is the data is actually blocks of disk data in the buffer pool. And if you want to access a record, you've got to find the right block in the buffer pool, indirect through a header on the block, find the record you're looking for, decode that record because it's not stored in main memory format. And when you do an update, you have to do the whole thing over again in the other direction. If you've got a cursor open on a block, you've got to pin the page so it doesn't get thrown out of main memory. All of this stuff consumes lots of overhead. It's about 1/4 of all cycles is to manage the disk buffer pool. Second thing is, in every single Elephant product does row-level locking. You touch a record, you set a read lock. You update a record, you set a write lock. There's a lock table. And so every time you do anything, you got to set a lock. And of course, you got to detect deadlock, all the standard stuff having to do with dynamic row-level locking. That's about an equal amount of overhead. And you can say, if I touch a main memory record and I touch a main memory data structure, updating it to put something into it, there's no reason why you'd think of those as grossly dissimilar in cost. So the third thing is every Elephant's database product, when you do an update, you write a log record in a write-ahead log. So that's so that you can do crash recovery if you fail. And so you have to write the log record before you write the data. That's a disk write. All the current products do group commit so that you and a bunch of other people all commit at the same time. So you share the latency of a disk write. But recovery code at runtime is another big chunk of overhead. And the last one is kind of a little bit surprising, and that's latching. Because, in fact, all the database products are multi-threaded. They're multi-threaded because historically, if you were going to do a disk read, well, you had to wait milliseconds for the data you're interested in to come back from the disk. In the meantime, you want to run somebody else. So they're all multi-threaded, which means there are K parallel transactions going on. And in a multi-core world, the idea is you can chew up all the cores that you have. But the problem is that B trees are a shared data structure, and you let multiple threads go wandering around and updating B trees, you can quickly trash your data. So you've got to latch the data structures that are shared, and that includes the end of the log, B trees, the lock table, resource allocation tables. They're all over database systems. and they all have to be latched in a multi-thread world. And just latching and unlatching all those data structures and dealing with waiting when you have to block when somebody else has the latch, that's another big chunk of overhead. So that's where the cycles in fact go in OLTP on the current Elephants products. So you scratch your head for a minute and a few things just jump out at you. The Elephants are slow because they spend all their time on overhead. It's not that they are bad at useful work, they just have all this overhead. Now, you want to get rid of that overhead, you're going to have to rewrite that Elephant code line completely. You're not going to make a disk-based system look like a main memory database system without huge changes to the code. So this stuff is all over the codes of the Elephants. It was all a good idea in 1985, but it can be violently beaten today with other ideas. So that the Elephants are going to have to rewrite everything in order to get rid of all of this overhead. So they're slow because they have legacy code, which has assumptions built in that aren't a good idea today. So to go a lot faster, you've got to focus on overhead. Focusing on building better B trees is going to do next to nothing. That isn't the high pole in the tent. The second thing you've got to realize is, for example, Oracle has a main memory database system called Times 10. However, Times 10 is legacy code also. It was written in the 80s. So it does dynamic row-level record locking. It has that piece of overhead. It writes a write-ahead log. It has that piece of overhead. And moreover, it's multi-threaded, so it has the latching overhead. It gets rid of the buffer pool overhead, absolutely true, but the other three pieces still remain. So if you get rid of any one of these four pieces of overhead, you only run marginally faster because the other three are still there. So you want to go a lot faster, you got to deal with all of them. And dealing with anything less is only going to give you an incremental improvement. So what I have ended up saying is in OLTP, the Elephants are up against a big problem, which is they got to rewrite everything in order to go a lot faster. And I could go through the other markets and show you the same thing, but in the interest of time, just take my word for it. They're up against rewrite everything in various vertical markets, and the ideas on how to go a lot faster vary from market to market. In OLTP, you've got to do this stuff. In the data warehouse world, you've got to write a column store. So they've got a major rewrite in multiple dimensions. So there is a wonderful, wonderful book by Clayton Christensen called The Innovator's Dilemma. If you guys haven't read it, I would highly recommend you read it. Basically, all of the legacy system software vendors are up against the innovator's dilemma in spades. So let me just tell you quickly what it's all about. Basically, if you're the market leader with an obsolete technology, it is almost impossible for you to switch to the new technology and not lose your customer base in the process. So it's really, really difficult. Even if you see it coming, it's really difficult to make the business process work out right. So I'll just do one very quick example, which comes from Christensen's book. Many, many years ago, there were steam shovels, and they were cable operated. There were cables that that went up over the thing and down to the bucket. So the high-end steam shovels were all cable operated. And they had a big problem, which is if the cable broke, the cables swung violently and people got killed. So they were slightly dangerous. And so a long time ago, I can't remember exactly when it was, hydraulics started to come into play. So people said, well, let's build hydraulic steam shovels. So initially, hydraulics weren't very good, and that you couldn't build big steam shovels with hydraulics. you could only build little backhoes. So the cable steam shovel guys said, well, this stuff doesn't work in our market. So other new companies came into existence that started building backhoes. And so people started to trench water lines from houses to the street using these little backhoes. So little jobs started to be done with backhoes, and there was a market for little hydraulic backhoes. Of course, what happened, you can just see it coming. Hydraulics got better and better, and it's way safer than cables, because if the hydraulics fail, the bucket just sort of slowly falls to the ground. So they were safer, and of course in time, hydraulics grew up and got to be just as good as the cable guys. And so of course the cable guys all failed and got replaced by the hydraulics guys. So that's the innovator's dilemma, which is it's really tricky to switch to a new technology without giving up your market during the transition. So all system software companies, including all the legacy database companies, are up against the innovator's dilemma in spades. So it will be really interesting to see how they deal with this, because in multiple dimensions, there is wildly better new technology. So the most likely scenario is that they're on a long-term drift into the sunset unless they can solve the innovator's dilemma. So anyway, in new OLTP, the elephants are not competitive. If you want to run at the low end and you want to pay a lot of money, by all means, run the elephant's code lines. If you want to save money, run open source. At the high end, they simply aren't anywhere near fast enough. So let's switch and start skewering the NoSQL guys. Another one of my favorite topics. So what they believe in is you want to give up SQL, ergo the name NoSQL, and they want to give up ACID. And the whole idea is to get scalability and performance by giving up these things that they perceive as expensive. So let's start with SQL. Well, they are completely misguided in thinking that SQL is the problem. In the case, we went through the case of where the overhead goes. I never mentioned SQL as a piece of overhead. The reason for that is that every vendor on the planet compiles SQL at compile time into the same low-level utterances that the NoSQL guys expect you to code directly, and compile time overhead doesn't count. So basically, 30 years worth of relational database experience is high-level languages are good. It is hard for you to beat the compiler that's running on your behalf. High-level languages give you data independence, less code, all kinds of goodness. And none of you write IBM assembler anymore. You all write in high-level third-generation languages. There's no performance reason why you shouldn't run database management systems with high-level languages. Second thing is that if somebody asks you to write a sequence of get next commands, the minute the data is on a different node than where you are, that will turn into a message per get command, which is just going to kill you. In the mid-1980s, Sybase figured out that stored procedures were a really good idea, and they really helped you performance-wise. So stored procedures are good, and the minute you have the detailed code in your application, you don't get a stored procedure. You want to move the transaction closer to the data rather than bring the data to the transaction. So anyway, high-level languages are good. If anything, they are performance faster rather than performance slower. The NoSQL guys are just completely misguided in thinking that this is the reason why relational database systems are slow. We went through why relational database systems are slow. It is not SQL. Okay, So that leaves us with acid. There's no question that acid is overhead, because on our pie chart, dynamic locking, which is a piece of acid, and right-ahead logging, which is a piece of acid, are significant sources of overhead. So they recommend giving up acid in order to go faster. Now, I just want to note quickly that the minute you are a disk-based NoSQL system, you are running a buffer pool, and you are subject to that quarter of the pie of overhead. All of these guys are also multi-threaded, and you are subject to that piece of the pie also. So they are not solving all four of these pieces of the pie, so they're not going to go wildly faster. And so giving up acid, will help you in performance. But I just want to make note of, acid has been the gold standard of data management systems for 40 years. Why is it? It's because people want acid. Why do they want acid? Well, we have a couple slides on why that is coming up. So if you need acid and you're running on a database system that doesn't support it, you get to implement acid in user code, and that is really a tear your hair out exercise. So you will end up doing a huge amount of very tricky code at user level, and I wouldn't wish that on anyone. Moreover, database systems last a long time. IMS is still an awfully popular data manager, even though IBM hasn't been selling it actively in a quarter of a century. So how do you know that you won't need acid tomorrow just because you don't need it today? So in my opinion, acid is goodness in spite of what anybody else says. So why do people want acid? Well, let's say I want to move $10 from account A to account B. Either both of those changes happen or neither of them should happen. If one of them happens and the other one doesn't, then somebody is out $10, either me or the bank, and those are both undesirable outcomes. So anytime you're moving something from X to Y, whether it's money or anything else, you need acid. Anybody who has integrity constraints. My favorite example is if I want to buy a widget and a widget holder from an online retailer, and I get the widget, if the second transaction is the widget holder and I'm notified that's out of stock, then I don't want the widget. It doesn't do me any good. So I want to be able to buy both of them or neither of them. Now, Amazon gets around this problem by, say, usually ships in 24 hours. What that means is Amazon's not going to guarantee you that it's in stock. And so if you actually want to know when you get the last widget, then you need transactions. And so anybody with a multi-record state, if I have an electronic game and I want to be able to move and shoot at the same time, that takes transactions. So ACID is required in just a huge number of applications, and giving it up is something I think you shouldn't do lightly. Now, I said that by and large, everybody wants HA. So the NoSQL guys make a big point about what they call eventual consistency. So what that means is that, let's say I have a database in Boston, and I have exactly one widget left. And so I sell it to Tim, and then I fail before I manage to notify my backup, which is, say, running in San Francisco. So San Francisco still thinks there's one widget left. And so I'm down, so I don't get to say anything for a while. So somebody else comes along, Eric Allman comes along, and he buys the widget from San Francisco. I've now sold the last widget to two different people. And eventual consistency allows this to happen because there's no guarantee of what's happening, in between things. So if you don't like the idea that you can have -1 inventory on widgets, you need ACID and replication, and eventual consistency will have the effect of creating garbage, because it will mean that you think the inventory is -1 and clearly is not -1. So technically what this means is that if you have updates that don't commute with each other, meaning that can be run in either order, then you get into this problem. I've just given you a simple example. So the minute you have two transactions which are order sensitive, then eventual consistency will mean creates garbage, or can create garbage. What are examples of non-commutative updates? If I multiply a number by 2 and you increase it by 5, it turns out that multiplication and addition don't commute. So you get different answers depending on which order those two things are run in. So eventual consistency is peddled as a great thing. In fact, in the vast majority of all application cases I can think of, it means can create garbage. And what that means is that you and application logic have to somehow sort out the mess. So the NoSQL summary, in my opinion, if you don't need transactions, then the NoSQL guys don't give you transactions, so you may be happy, at least for now. They will work most of them will work if you have single record transactions that are commutative. The minute you get outside of that small little bubble, they're going to have significant semantic problems. In my opinion, they're not a very good fit for new OLTP, which wants high-level languages and ACID. So I think NoSQL guys are good at lots of things. Mongo and Couch are very good at document management. Neo4j is great if you've got a graph management problem. But I think in general, these guys aren't good at OLTP. So you should use NoSQL systems for what they're good for and not use them for what they're not good for. Now, I think it's kind of interesting that recently there have been two proposed higher-level languages. CQL, which comes from Cassandra, and Uncle from Mongo. And unless you squint, those look exactly like SQL. So the NoSQL guys are moving to high-level languages that are SQL. So it seems to me that my best prediction is that the NoSQL guys will move fast toward standard high-level languages. That means SQL. And they will be pushed kicking and screaming into supporting ACID. So they will move toward relational database semantics and not away from them. So that's just my strong suspicion about what's going to happen. Okay, so I'm done dumping on NoSQL. Now let's move to another cast of characters. So there are a bunch of startups that are saying preserve SQL, preserve ACID, but go fast somehow. Go fast in light of the pie chart that we just saw. So VoltDB, the company I started, is one. Clustrix is another. Akaban is another. NeoDB is a fourth one. So there's a bunch of startups that are in this space that are saying SQL is good, ACID is good, figure out how to go way faster than the elephants with some very different implementation. So what does that mean? Well, you cannot do record level locking and go wildly fast. That's simply not going to be an option. So you have to do something else. And there are a bunch of ideas that have been floating around in the space. What VoltDB does is it does transactions in timestamp order with no locking whatsoever. Optimistic concurrency control, multi-version concurrency control. There are a bunch of other ideas. Do something other than row-level, record-level locking. Second thing is you've got to be a main memory database system, or you're going to be subject to that piece of the pie that's called buffer pool overhead. So at least the obvious thing to do is to do a main memory database system. And you can certainly be clever and say, I can have your hot data in main memory, and I can make the rest of your data really slow and not in main memory. But you've got to be dramatically tilted toward main memory. In particular, you've got to store data in main memory format, not in disk format. And maybe there's some other way to reduce buffer pool costs, but I don't see what it is. But I'm certainly open to somebody having a good idea in this area. You've got to have a solution to latching, because that's going to kill you. And off into the future, as we see more and more cores, as Intel tries to sell us more and more cores in a single socket, this latching problem is just going to get worse and worse and worse. And so if you're running a multi-threaded database system with a lot of shared data structures, and somebody gives you 100 cores that are sharing main memory, you will use about 3 of them, and the rest of them will sit blocked on your latches. So to make headway here, you've either got to be single-threaded somehow, you've got to have some innovative way to not latch all your shared data structures. So there's some interesting innovative uses of B-trees that try and avoid latching blocks of B-trees when you do updates. And again, your good idea goes here. The obvious thing to do is to be single-threaded. So I'll have a slide in a minute to say how can you deal with multi-core if you're single-threaded. So hang on to your seatbelt. You need a solution to write-ahead logging, because that's the other big piece of the puzzle. And the obvious answer is to automatically build in HA. The OLTP guys want it anyway, so just provide it automatically, which is everything is replicated, you automatically fail over. You never recover from the log, because OLTP guys don't ever do that anyway. They fail over and keep going. So build in replication and fail over, and don't have these detailed write-ahead logs that are in the legacy vendors' products, because people don't want to recover that way anyway. There's a whole bunch of details about exactly how you do replication, fail over, and fail back. And so any given vendor who says they have this, you need to ask them a whole bunch of questions. Do they fail over online, or do they go down? Do they fail back online when you repair your hardware, or do you go down? Is this a LAN environment? Is this a WAN environment? Is this both? And so forth. So a lot of questions you ought to ask. So Volt is an example in this category. How do we do things? Volt is a main memory database system. There is no disk assumed to be there. So all data is stored in main memory format. The way we view the world is that in main memory, if you look at TPCC, an extremely heavy transaction would read or write 200 records. That's a very heavy OLTP transaction. In main memory, the useful work to reading and writing a couple hundred records is measured in microseconds. There is absolutely no reason to deschedule a transaction that runs for, say, 50 microseconds to run something else. You simply want to run stuff to completion without interruption. So VoltDB runs single-threaded. It runs transactions to completion in timestamp order. There is no locking. There is no latching. Those two pieces of overhead completely go away. And as I say, VoltDB builds in HA. So this replication is the way to recover. All OLTP systems want to use replication and fail over anyway. So there's no log, at least not in the traditional sense of the word. So you might right now say, how can you be single-threaded if I have 10 CPUs and you're single-threaded, then what are the other 9 going to do? So the answer is, in Volt, if you give us K cores, we will divide main memory statically into K non-overlapping buckets and assign main memory statically to cores, so that we will pretend that your K-core CPU is in fact K one-core machines which don't share main memory. And so that's what we do. There may be some better ideas. So you convert multi-core into K single-core machines in order to get rid of the latching problem. Okay, so where does all the time go in Volt? The answer is you get rid of the overwhelming majority of all 4 of these pieces of overhead, and that's how you go really fast. There is a small amount of synchronization that does remain, but by and large, Volt is violently faster than the Elephant systems. So the current status of Volt, here's the one slide and the message from our sponsor. It runs a subset of SQL. If you want to run correlated subqueries, we don't do that yet, but we're getting there. We run on clusters. This is Linux-based, TCP/IP-based. We are hardware agnostic. Run your favorite cluster, whatever that is. We do LAN replication. We fail over, we fail back. We're working on WAN support right now. It's not quite there yet. And we've run TPCC against one of the popular Elephant's code lines. This is somebody with more than 3 letters in their company name and less than 9. And we run about 50x what they run on TPCC. So not quite 2 orders of magnitude, but pretty close. We've run against some of the NoSQL vendors. So we've run Cassandra, and we're less than 10x faster than Cassandra, but more than 5x. One of the popular NoSQL data models is key value store. So there's many of the products that say, we'll give you a data model which is key and payload. Well, to a relational database system, key and payload looks like a 2-column table. And the key value guys say, I'm going to give you get, put, new, and delete. So there's basically 4 stored procedures that implement what the key value stores do. And you can run those as 4 stored procedures on a 2-column table. And Volt does exactly that. So we have a key value simulator. So if you want us to look like Memcached, we look exactly like Memcached with this little veneer. And against Membase, we are somewhat faster than Membase, which is Memcached connected to Couch. So this is wildly fast against all comers. How does it scale? Well, we're a startup. We don't have $1 million to buy a really high-end machine. So this scales to 384 cores, which is the biggest iron we could get our hands on. And by the way, this is an open source system. So I'm a huge, huge fan of open source, not for the reasons that you think. To me, open source is a good idea because I've worked with or for database vendors for more than a quarter of a century, and it really pains me that all the systems with proprietary code lines hire 4-legged sales teams. So there's a salesman who you pay really big bucks to, and he's only smart enough to take the customer to lunch. And so you pair him with a system engineer, an SE, who also gets paid big bucks, who is technically competent, and you send these 4-legged sales teams out to make sales. And the average enterprise database vendor spends half of your money, your license money, on the cost of sale because they've got this really expensive object called a 4-legged sales team. I hate this sales model because you're just wasting everybody's money. So open source means that you guys get to be your own salesman. So, and it wildly knocks down the cost of sales and therefore facilitates just way cheaper prices. So I think it's just a way more efficient sales model, and I think it will prevail over time because every database system written recently is open source, and open source for this reason. So my summary, in the OLTP world, the old world was the human as intermediary is sitting there typing on your behalf. That's completely gone. It's now a web sensor world. Old SQL, the legacy vendors are just way too slow, and lots of them don't scale. NoSQL has no ACID, and it requires you to code in database assembler language, which I think is a terrible idea. The high-level language debate between Codicil and relational systems, that happened in the 70s. That's really old news. And everybody should be forced to read about history or they will be condemned to repeat it. So low-level interfaces are not a good idea. NewSQL, I think, is fast, it's scalable, and it makes use of totally different architectures than what the old SQL guys do. So thank you. That's the end of my slides. I hope I've made somebody mad by now so that you'll ask some questions.
So if I take Amazon as a poster child for NoSQL, although it might mean not just SQL, and for eventual consistency, and I accept your thesis, then is the outcome that Amazon is going to be doomed finally because it will run out of programmer capacity to fix things?
Okay, so the first thing to realize, there's a bunch of lessons. First one is that Amazon, you don't hit a database system until you say buy it. All of their catalog management stuff, all of their shopping carts, all of that stuff is not database applications. When you say buy it, you hit an Oracle database. So they are running old SQL right now. At least they were as of a year ago. Maybe there's somebody from Amazon here that can correct me. So they're currently running old SQL and are managing to keep up. They have a data warehouse that has their historical buying patterns so that the business analysts can run on that. That's also running on old SQL. So they are running a traditional shop. They did implement SimpleDB, and I'm not quite clear what they're using SimpleDB for, but it was basically written for, it was a purpose-built application. So most of the web properties have built purpose-built database systems. So Cassandra was written by Facebook, Bigtable was written by Google, ... So most of them have simply rolled their own. And the reason they have rolled their own is that if you're running at the unbelievable volumes they're running, the build versus buy decision is tilted toward build, especially if you've got highly competent programmers. So the big web properties are generally rolling their own database systems because they're at a volume and have personnel that's the cheapest thing to do. There are only six companies on the planet who are in that state, and the rest of us aren't going to build, we're going to buy. Does that answer your question?
Hi. Shiri Cabral from Mozilla. I have two questions for you, so I'm going to ask one and then ask another when you're done. You said that in your little graph about VoltDB, it showed that there was absolutely zero buffer overhead. And I was wondering, buffer pool overhead, how does that happen when you have, there's got to be some memory management when you're splitting up your buffer pool into one per CPU.
Okay, this gets down into exactly how does Volt work. So Volt runs across k nodes, and we partition logically tables with range partitioning or hash partitioning. And so there are partitions. They are in main memory format. And yes, there is communication overhead. So when you add CPUs, you don't get 1 times scalability. You get 0.9 times scalability. And so, there is some overhead to, as you add machines. But we basically scale linearly with a slope of about 0.9.
And then my other question is, at the very beginning, you said that there wasn't really a benefit to working on newer and sexier B trees, and yet if you improve the B tree latching, wouldn't you have a lot less of that quarter of the pie of latching? So would there be a benefit in working on that?
Oh, absolutely. In other words, if you guys want to work on something, don't work on making B trees faster, make them more concurrent. Because that's because the latching problem is the high pole in the tent. Absolutely, I think there's lots of room for innovation in making multi-threaded systems more concurrent. Because I think the elephants are going to have an unbelievable problem in this area, just unbelievable.
A lot of what you've talked about has been sort of speeding up things specifically for the OLTP applications where the database is small enough to fit on one machine. Some of the most interesting problems in databases these days are large scale, like really large scale distributed databases where, and I think the reason people have gone to NoSQL in a lot of cases is that problem. Do you have any thoughts on how that might be solved with VoltDB?
Okay, so here's my thinking. So people don't want to run OLTP on the same machines that they run data warehousing. And they don't want to do this because the warehouse queries are unbelievable resource hogs, and you don't want to interfere with OLTP overhead. So people run OLTP, and then downstream from OLTP is a petabyte data warehouse. So that very traditional wisdom is to separate these two functions on a different hardware and run an ETL system that copies data from one to the other. So the answer is there are a few OLTP systems that are terabyte sized. I mean, Facebook has one of them. Facebook has one of the hardest data management problems on the planet. If you're not in the terabyte range, then run a main memory database system. Volt runs over any number of nodes that you want to allocate it to, and so except at the very high end, I think main memory database systems are a good idea in the OLTP piece. Downstream is a data warehouse, which is unbelievable in size. So for example, Zynga, which is a big online multiplayer games system, they have an OLTP problem, which is maintain the state of every Farmville farm, and then they have a data warehouse which is something like 5 petabytes in size right now. And so if you want to run one single system that manages both of these, then you're going to run really, really slowly because, in my opinion, one size doesn't fit all. You can win by a factor of 50 or 100 by specializing each of these applications. So the data warehouse, run a column store. That will beat the heck out of any of the NoSQL vendors that are all row stores. And those guys all scale to petabytes, over hundreds of nodes. And in OLTP, run something that's a main memory database system. And unless you're at the very, very high end like Facebook, this will be very good advice. Because if I specialize my OLTP system, I run a factor of 50 faster. If I specialize my data warehouse, I run a factor of 50 faster. If I put them both together, it's going to mean a factor of 50 more hardware, in both areas.
I noticed that you benchmarked VoltDB against the old SQL and also against Cassandra, conspicuous by its absence when it was any new architectures like the Vertica database system or Greenplum. Have you thought about benchmarking against those?
Okay, so I think I'm a huge fan of specialization. Vertica, Greenplum, Parexel, Teradata, Asterdata are data warehouse systems. They are completely focused on storing your historical petabyte. They are terrible at doing OLTP. Don't even think about it. I mean, since I wrote Vertica, do not even think about Vertica for OLTP. It was never designed to do that. It is no good. It is no good at doing OLTP because they've totally focused on doing data warehouses and doing it well. Volt is absolutely no good at doing your historical data warehouse. It was never designed to do that. It is not a column store. It's a row store. It's main memory. Do not try and store a petabyte in Volt, unless you're willing to pony up a petabyte worth of main memory. So I think specialization is a really good idea because it means you can go a lot faster in some vertical market by specializing your architecture. And the good data warehouse guys are very different than the good OLTP guys. They're just oriented toward a totally different market. So I think off into the future there will be half a dozen interesting database architectures. There will be column store data warehouses. There will be main memory OLTP systems. There will be document management architectures like Mongo and Couch. There will be graph database systems may well make it, and there may be a couple more. There'll be array database systems for the science market, and each of these architectures is a factor of 50 or 100 faster than a general purpose system in their vertical market. And in each case, do not try and use the specialized architecture for anything else because that's not what it's good for. So I think that's the world that is fast approaching.
Hi, Eric Coleman. So you like the specialization, but the data often has to be moved from one place to another, which is usually an ETL operation, which can be very expensive and means the data in the warehouse is, except for a few microseconds, out of date. How do you answer that?
So I think, absolutely true. And I think the answer is, if I'm running a query over a petabyte database, whether it's 3 seconds old or instantaneous, I don't think matters. So I think it's not the latency that's an issue. There's no question that ETL is expensive. It's another moving part. As often as not, your data warehouse schema is different than your OLTP schema, so you've got to do that transformation somehow. And real-world production enterprises do not want to mix the two kinds of things on the same hardware for response time reasons anyway. So I think it's going to be a long time before the two different systems and ETL goes away. And I think my point of view actually is that there's a great market opportunity for somebody to put a nice seamless layer on top of his favorite column store and his favorite main memory OLTP system that includes the ETL so it all happens seamlessly and automatically and recoverably, because database administrators do not want to deal with moving parts.
So I know you've worked on stream databases, for lack of a different word. I actually expected that to be your answer. Is there some reason it wasn't your answer?
Well, I think I think an interesting answer is that I started a company called Streambase that does stream processing, a company called Vertica that does data warehouses, a company called Volt that does OLTP, and a company called Paradigm 4 that does array data processing. If those were all one company, that would be a really powerful, that would really be quite something. The trouble is that when you're a startup, it really pays to focus. And Vertica originally started Volt as their second product, but spun it out because of focus. Well, during the Lehman Brothers collapse, it was called Hunker Down. So I think if there were a way to do it again and raise 6 times the amount of money and put all of those together as a in a single environment, that would really be a good idea. But we're not there. I'd love to rewrite history or find some way to have managed to do that. Maybe some enterprising bigger company will buy all these companies and do that.
Yeah, they'd probably make a complete hash of it. So I'm very much into the open source thing, but I'd also like to find out what the revenue model is for companies that are doing that. So what is Volt doing to?
I think the revenue model is absolutely straightforward, which is look at Red Hat. So Red Hat has an enterprise edition that has a bunch of goodies in it that are not in the open source version. And so everybody will have an enterprise version and a community version. The community version is free, and they will try and put enough goodies in the enterprise version that they'll get you to buy it. And then support usually only comes in the enterprise version. So they will bribe you into running the enterprise version. And the free version is basically a sales tool, effectively. But the good news is that the enterprise version is wildly cheaper than the proprietary guys charge. So the whole price structure just goes way, way down. But anyway, the answer is an enterprise version, sell support, but get people to buy the Oldsmobile rather than the Yugo. Great. Thank you very much.